Okay, a wonderful good morning, everybody. I hope you're well. We start our day here in the Cobos with a wonderful talk from crypticcelery about computer graphics, and we start.
So, essentially, a few people told me to pour my info dumps into a talk, and this is it. So first of all, a little bit of content warnings. I know it's early in the morning, but this talk will contain some math. It will be cursory, but there will be math. And also on a more serious note, there is one little image that might be a little bit disturbing. You might have already seen it regarding Assassin's Creed Unity. I will bring it up before we show it. Otherwise, this should be fine. So let's first look at what we're dealing with here, or why I'm doing this. I'm really interested in this topic because on current hardware, modern computer games and engines can create pretty amazing visuals like this from Cyberpunk 2077 or Baldur's Gate 3, or in this case, Horizon Forbidden West. And the thing powering all of these, like the rendering part of this, are GPUs, graphics processing units, and they're pretty impressive. So if you look at something semi-recently, an RTX 4090 has roughly a throughput of floating point operations of 82 trillion per second at precision of 32 bits, which is a lot. As in, if everyone on Earth per second would make one calculation, you would need about 10,000 Earths to have like the same kind of processing power. And part of what we're digging in here to is how can they do that? And the key term, bring it up again, is embarrassingly parallel. So a problem can be considered embarrassingly parallel if you can just split it up into tons of little pieces without little thought or communication in between those pieces. And this is going to be the first part of the talk. How can we make rendering 3D scenes embarrassingly parallel? And it's like, how can we display objects, which will be rasterize them, shade them, and a little aside on more recent advancements of real-time ray tracing. And after that, we'll branch over to the actual hardware implementations of those things, cursory look at the history, and then primarily like, how do they work, what are the limitations, and some more specializations of the hardware. So let's get started with the rendering itself. So simple approach would be just to use sequential rendering, so just use the CPU to display something. To illustrate,
sequentially, one after the other. In 3, 2, 1. Let me speed it up.
Yeah. I think you can already think that's not going to cut it for more modern visuals where you're thinking about cranking out at least 1080p at 60 frames per second, possibly more in either dimension. So we need to decompose things to make it a little easier. And the first thing where we break it down is we just say everything is triangles. It's all triangles. They are very simple geometric primitives. They are always in one plane. If you have like 4 points, you can have weird shapes that you don't want to have. So we're using triangles. To introduce some terminology, we say like one object that we're rendering is a model, and a model, for our intents and purposes, is an array of triangles. So kind of like an STL file. Each triangle has 3 vertices, and here we're working in 3D space. So each vertex has at least a position, which we will express, this is where the math begins, as a vector. And the cool thing about vectors is you can use matrices to transform them to affect a lot of different things. This is a very simple example. I will not reiterate matrix multiplication here, but this just is the identity matrix, which just returns the same vector upon multiplication. And The next term we need here is model space. If you just like have one specific model, either from an STL file or any other format that, for example, might include textures or additional metadata, you're working in model space. This is all just in relation to one another in the model. So if you were to just like put a lot of objects into the same spot, they would all overlap, which is not what we want. So we want to be able to transform this. A very simple transformation is scaling an object. You can scale it uniformly or scale it across different axes. And the math behind that is also relatively simple. You just multiply the axes. Because you're essentially working from the center, you can just multiply each coordinate by the scaling factor you want, and you're done. So, a little more advanced, rotation. If an object falls down somewhere or someone just turns around, you of course want to rotate it. You can do that along single axes as the simple case. So just using trigonometry, this would be the 2D rotation case of just rotating a vector around, like if you're doing it on paper, an imaginary third axis. And this just translates well to the third dimension as well. So you will just leave alone the axis you're rotating around. So this is a rotation around the x-axis, which will modify just y and z coordinates. There is a little bit of a problem with these approaches, is that if you're just using so-called Euler angles along separate axes, you cannot interpolate them nicely. Or you need to do a lot of additional work to get that working nicely. So if you're thinking about you have something at 10 degrees and something at 350 degrees, you want to take the shortest path here. And there's some additional problem that come in here where along certain rotations, another rotation doesn't do anything anymore. This is called gimbal lock. And there is actually a relatively nice way to get around that. And it's deeper math magic called quaternions, which are essentially an extension on the complex numbers, or but for our intents and purposes are kind of points on a 4D unit sphere. So these are always normalized vectors, but they can be used to express rotations, and this is out of the scope for this talk to explain how this works. But you can then transform a quaternion relatively simple into a rotation matrix, and the cool thing about quaternions is they can be interpolated nicely and they will always result in a smooth rotation from one point to the other, which is really useful for animations or anything moving. And finally, we can scale things, we can rotate things. Now we just want to place things at different points maybe, and this is called translating or translation. And this is how we've been doing it so far. It's a little bit of a challenge because there's no 3x3 matrix that can express a translation. These so-called affine transformations are limited here. And this is where we start to cheat, which is a theme that's going to come up a lot in real-time rendering. We add the fourth coordinate, and we set it to always 1. This is called the homogeneous coordinate. And the cool thing about this, we can just use it to express translations by just multiplying it by the translation coordinates we want to achieve. And this matrix will affect the translation. And importantly, you leave the homogeneous coordinate as it is. Otherwise, weird things start to happen. So we can perform the most important transformations. We can translate things, we can rotate things, we can scale things. And since we're working with matrices here, they can also be multiplied with one another to combine transformation. And conveniently for us, matrix multiplication is associative. So you can just combine all of this into a single matrix that we will call the model matrix, which essentially transforms a model from model space into world space, which is the actual scene we want to render. Now, we have objects in a scene, But there is one thing that's missing. Any idea as to what? Yeah? Camera? Yes, the answer is a camera. The answer, sorry. You need to have a viewpoint in that scene, especially if you want to move through it. And this is also a little bit more advanced math that's going in here, so we're going to abbreviate this a bit. So in essence, you typically have a camera at a specific coordinate, looking at a specific point, or analogously with a certain rotation. The typical look-at transformation uses a from-to and a point up, so you can actually roll the camera. And you can use that to construct another coordinate system. So instead of like your just x, y, z centered in 0, 0, 0, you can move everything related to the camera, which we call here forward, up, and right. And basically simplified to transform something to another basis, especially if your original basis is just the normal x, y, z, you can just use the separate basis as your matrix values to rotate everything so it is essentially pointing at where the camera is, or how the camera would look at it, and to finally then look at a specific point or have the view matrix to encapsulate your viewpoint. You would again also translate everything relative to the camera, so you also handle the position of the camera. So if the camera moves, everything in the world moves from your perspective. And that's the next key point, perspective. Now we have objects relative to the camera and know where they are. But if we were to just kind of render them now, you would end up with what is called an orthographic projection. Here, this is kind of comparable to a drawing of a building for construction purposes. So you're seeing it from the front without any perspective distortion. And this involves a typical, like another matrix called the perspective matrix. And that is usually defined by the aspect ratio and field of view of the camera you're trying to simulate, and also something called the near and far clipping plane. These two planes essentially encapsulate the view of the scene you have, especially since you're working with floating points. You don't want to have too large of a thing because it becomes inaccurate at certain edges of the so-called view frustrum. The view frustrum is essentially the area between the near and far clipping plane that the camera would see and fully render. And analogously for an orthographic projection, the view frustrum is just a cuboid. And this is where the perspective division comes in. After you apply all of this, you essentially divide by the distance from the camera. Or to put it another point, you multiply by the inverse of the distance from the camera. So the further something is from the camera, the larger it is in x and y coordinates. So, the space is larger at that point. So if you're closer, it's smaller, and you see more of the view frustrum. You get it. It's okay. I'm hung up here. Sorry. Yes. So you divide by the distance from the camera, and essentially everything becomes smaller further away. And it becomes smaller, but it's more compressed in your view space. So I can see more further away. So at that point, the x and y gets smaller. Sorry. But to wrap this up, we have a set of different coordinate systems that we're bringing our models through. So we start with the so-called model or local space, which we transform into a world space or scene using the model matrix. And then using a view matrix, we end up in view space, which is orthographic. And then we apply another projection matrix and the perspective division, if we want it. to end up in so-called clip space. This is normalized from -1 to 1 in all dimensions. So we just perform some simple rescaling operations to bring it into screen space, which is just the screen coordinates. And that would be something you can see on your screen. And we could render that. But here we come to the first problems. We need to optimize this a little bit, because what you're seeing here is a lot of triangles, like a whole lot, and many schemes are very complicated. So we need to optimize some things. And a very simple optimization that saves you half the work in most cases is called backface culling. If you look at an object, you will usually never see the backside of it. And we can just encode that into convention. So we just say, for like any model, we say the vertices of each triangles should always be wound in counterclockwise order. So it's, from your perspective, would be 1, 2, 3. And based on like how we're encountering them, when processing them, if they're the other way around, we know that's the backside of something. This is where the slightly creepy image comes up. This can go wrong. And it can look somewhat like this if that happens. This is one possible cause here, that somehow the desired winding order of the triangles was not specified correctly. But it could also be that the face mesh didn't load. But that's a very good example of, you see the backside of some things here. And you don't want that to happen. So we saved half the work now. There's a lot of other things you can do, like reducing the level of detail of objects that are further away, but that's more like implementation specific. So next we come to the step of turning our triangles into pixels, which is called rasterization. So we have our vertices, which encode a triangle, and we want to figure out which pixels are covered by this. And how this works is relatively simple. Again, we're trying to break it down into simple things. We trace each line and in screen space lines. So we start at one vertex and follow it along, placing pixels, or so-called fragments, which encode like this whole line or this edge. And we do that for the whole triangle. Technically, in most implementations, triangles are usually split by a horizontal line, because that way you can just start walking from both top directions, and each time you move vertically, you can fill the line in between, and that way you've identified all pixels and it generated all fragments for this triangle. Rasterization or line rasterization, there's a lot of different solutions for. A common one is the Bresenheim line algorithm, where you just try to walk up as far as you can and place before moving beyond the line, and then continue working right, and you generalize that for all different line directions. So now we can just place differently colored triangles in a scene. And that's admittedly a bit boring. So we want to add some more color to it. And one thing we can do is, given that we have our vertices and know how long we've walked along the edges of the triangle, we can interpolate values between the vertices. So in this case, we're interpolating color. And color can just be expressed as an RGB vector. So we can also interpolate any kind of vector. So for example, a two-dimensional one, a position. And this is where we get to texture mapping. As a simplistic example, if you have a triangle that is part of a cube in a scene, you can, for each of the vertices, for your model, store the coordinates of the texture you want to render at that point. And then for a given point, you can interpolate between the two lines, the two edges you're walking along, or the vertices of these, and then interpolate again between those two things, which is what happens if you're walking along the line between the two fragments you're emitting. And that way, you know a coordinate where to look in the texture to find the color you want to render here. And this is just a 2D vector. Typically, these are called UV coordinates, which is where the term UV maps relate to. A cube is relatively simple. Most UV maps are somewhat more complicated, but the principle is the same. Because you're just interpolating coordinates, and it's just the edges and faces here just represent real edges and faces. Oh, sorry, real edges and faces in the model. There's a few more problems with this. One thing that could commonly happen on like the simple implementation of this is aliasing. If you're looking at something further and further distanced, at some point you're gonna for each pixel that you're moving, move much farther in the underlying texture. So something that's far away is smaller. So it would you would end up doing a lot of little jumps, and for example, a checkerboard texture would start to get these kind of more artifacts over here. But there's a solution with that is called MIP mapping. And the idea here is for each texture, you just usually at runtime generate just not double, but like take 50% extra space to just store downsampled versions of that texture in. And by just downsampling it by half each time until you end up at just a single pixel. And then, given by the fact while rasterizing, you know how far you're moving along the line, you also can kind of generate a derivative of the coordinates, the texture coordinates. So you kind of can, by that, estimate how large is the area you're sampling. And you can use that if you have, like, as a debug visualization, different levels of a MIP map to just determine, like, which resolution do I need to do here. And typically you do trilinear interpolation here. So you find the right, you interpolate the right coordinates of the higher level and the lower level MIP map, and then interpolate these sample results again, which is the fading areas you can see here. And you can also see if it moves further away from the camera and is not angled towards the camera, you get lower resolutions. And if it's still further away but angled towards the camera, it's flatter towards it, so you get a little bit larger resolutions. And that way you can account for these obstacles and can just apply textures to your scene. But now, thinking about rasterization, each of those triangles still generates a lot of fragments that you want to render and process. And objects in the scene are not necessarily ordered, so things occlude each other. So if you have something like, for me, the laptop is in front of the desk, in front of the podium, and I wouldn't need to render that part of the podium. And this is where the next large optimization comes in, depth testing. If you consider any scene with objects inside of it, like the ground in parts is obscured by the objects here. And what we do here is instead of just storing the color that is rendered for a certain pixel of the screen, we also store how far away it was from the camera in so-called depth buffers. And when we get a new fragment, we can just test, is it in front of what I've already rendered at this point? If yes, I overwrite it. If not, I just discard it and can save a lot of work. This can also have downsides called z-fighting. If objects are perfectly plane to one another, which can happen pretty easily, especially in a game, because they have the same depth, it kind of depends on like which one gets rendered first, depending on if you're doing a greater than or equals test for the depth buffer, and you get these z-fighting artifacts. Usually the trick is to avoid this happening or applying some biases here. But so now we would have everything to just like build a nice looking game, right? Well, kind of. We can add textures here, maybe add like simple opacity effects if you're being very fancy, but there's of course a lot more you can do with rendering here. And this is where we get into the next part, which is about shading. Because we can just apply textures to things, but how you work with those textures when finally processing the fragments is the big deal, where you can make differences if you're doing very physically inspired rendering styles or just some non-photorealistic styles like toon or cell shading. And this is a huge topic. I want to bring up this, that when the bulk of the work happens actually when processing the fragments emitted from your triangles. So, for example, a relatively simplistic model can be made to look much more detailed by applying so-called normal maps, which store the deviation in 3 dimensions from the surface normals of the triangle to the actual higher resolution model. So that's why you have these RGB kind of colors in the right image here, which can then be used for lighting effects when you consider how the light falls in and gets reflected. Depending on your camera angle, you can have much nicer effects here, like this very nice looking stair, these very nice looking stairs, which is the same model, just rendered with this effect applied. And another thing you might want to do in more realistic scenes is, if a light is shining into a scene, you also want shadows in that scene, which typically is where a light isn't, and that's not so easy to like correctly calculate. But again, we cheat. We already know, like, so if you're looking at the light source, very simplistically, the only thing that receives direct light from it is everything the light source sees. And everything behind that will not be hidden. It will not be illuminated by that light source, so it will be in shadow. So we just use depth buffers again. But this time from the perspective of the light instead of the camera. So before rendering the scene in detail, we take each light and just render the depth buffer from the perspective of that light. And when processing the fragments and shading them, we calculate the distance from the camera, from the light, and if it is in front of the first distance we've rendered in the first pass, it is illuminated, and if not, it is in shadow. This is, of course, a little bit of an abstraction, but it's good enough for most instances to have some nice looking lights. Technically, there's a lot more to that, and this is where we get into global illumination. If you're just thinking about, there's a white light cast into like this cube scene, which with colored sides, the reflected light from the sides will end up affecting the, bouncing around and illuminating lights further. And what you can also see illustrated here, you can approximate this in multiple passes of light bouncing around, but that is a lot of effort, and you can do that like stepwise, which you sometimes see in games where, like, when a scene rapidly changes, things fade around edges, fade for a few frames. This is just global illumination happening over time. But of course, there's nicer ways to do this, or like the correct way of rendering, which is where we get into ray tracing. Instead of just like approximating everything as we've shown before, in ray tracing, you usually from the camera just bounce simulated rays into the scene and let them bounce around randomly when they hit objects. And if they hit a light, you know that like this is the chain of illumination, and then you can then calculate like which color should this pixel have. And that way you can simulate a lot of different effects. You can see here with nicer reflections or light actually going through portals, which is more difficult to do with the real-time approaches we've shown so far. But there's also a lot of other effects that can happen around here, like caustics. Very simple example in the bright light outside. If you have a chunk and the light is cast through it, you will see like these very nice lensing effects. These are called caustics. They are very difficult to fake, which usually means you ray trace them. And you can also do area lights, because as we can see here, like we can do an orthographic projection from the sun, which is like kind of light all coming from the same direction. And we can do a point light, which is just like a perspective camera using to get the shadow map. But light that has an area like a neon light is much more difficult to handle. And this way, with ray tracing, you can do, we can actually work this. But there's of course a downside. Simulating all of these rays is kind of like non-deterministic and a noisy process and a lot of effort. So it takes a lot of samples to get a scene very nicely rendered using ray tracing. And well, that's not the time we have because we want to work in real time, ideally like at least 60 frames per second, for example. So here we turn to some optimization ideas. Roughly, the key primitive operation that is happening in ray tracing is ray triangle intersection. So you cast a ray into a scene, and you want to see like which triangles, if any, does this intersect with, because it's all triangles again. That's a very simple operation, but you have lots of triangles. So you also want to have like some sort of overarching spatial architecture data structure to see like to discard huge swaths of your triangles at the same time. So essentially divide and conquer. And this is where we come to bounding volume hierarchies. If you're casting a lot of rays into a scene, we can store a hierarchical data structure of different volumes that are covered by the covering different triangles, and that way we can quickly hierarchically traverse a ray through the scene and don't have to do thousands of tests that we don't need to do, which is called the BVH traversal topic here. But this is like the key optimizations you can do in ray tracing. There's a lot more, of course, beyond that, but again, out of scope. So that's after this huge block of theory in the morning. To recap, the big part here is the rendering pipeline. So you have your vertex data, which is the coordinates and also the texture coordinates, maybe some colors you want to also have in there, which gets processed by something called a vertex shader, which is a program you write and run on the GPU. To, for example, apply your the model view and perspective transformation. Then there's some additional steps of geometry shading and tessellation, which is out of scope here, but you can add a lot of stuff here and just like have low resolution models actually be higher for displacement mapping and other approaches. But based on those emitted vertices, you can assemble your shapes, rasterize them, and then the bulk of the work of making a scene look nice happens in the fragment shader, which processes each of those emitted fragments from the triangles, and after testing and blending for depths, etc., you end up with your full scene, which gets displayed on your display. And that is essentially how you break it rendering down to be embarrassingly parallel, which brings us to the next topic. How does this actually kind of look in hardware, and how does the hardware support this well? Don't forget to drink enough water. So, what is the embarrassingly parallel hardware we're working with here? To quickly recap, GPU specifically, started as like acceleration units usually deployed to simplify some processing aspects, especially since memory was extremely expensive in the early days. So having a lot of different frame buffers, which is like what you display, was prohibitively expensive. So you wanted to ideally generate things at the fly and quickly display them, for example, over an VGA cable, which is literally just like, this is my colors, and now switch the line, and now switch the line, as in analog signals. And over time, this of course evolved, needs changed, different accelerators cards come up, and we kind of now end up at the colorful, chunky bricks we have today that also sometimes catch fire. A hopefully not. Depends on how you connect them sometimes. And we're mostly talking about these modern GPUs, essentially completely, because that's the most relevant now. So the hardware we're looking at is, or these chunky bricks, typically is mostly a heatsink, but still similarly constructed. So you have a PCB where you have the key component, the GPU die itself, surrounded by some memory for quick access, power management, and I/O to connect it to your PC, power, and displays. And zooming in on that, this is kind of what one of those dies would look like. I think this is not a photorealistic die shot, but I'm not entirely sure. But to work more effectively with this, this is a schematic representation of the same thing. To make this a little bit more easy to see, let's rotate that. And the key components here is, besides I/O for memory on the side, it's a bit difficult to read because sadly these are the nicest schematics you can find, and NVIDIA doesn't really provide high resolution things for those. Memory interface to their cross-talking solution, and of course talking to the PCIe. Then you usually have a huge cache and lots of separate modules that are structured hierarchically. And here the terminology diverges a bit between the different vendors. So for example, NVIDIA calls these smaller units we've seen here graphics processing clusters, which then have texture processing clusters, and below that streaming multiprocessors. But that's just hierarchy and architecture specific. Usually these terms are not necessarily that necessary. And what you can also see here is they have a specific hardware block for rasterization that just handles that part. But what we want to focus on here is the streaming multiprocessors, which the workhorses of what we're working with. And just, if you don't prefer green, these things look very similar. If you prefer red, on the left you have the full overview, and on the right you have a more detailed drill down into one compute unit, etc. And also, if you change the color to blue, it's also very similar. So most of this translates. It's just the naming and the structure is a bit different, and the background color. But the core unit, what we want to work with here, zooming further into the streaming multiprocessor, are the actual cores that do the work, and something that NVIDIA here calls warps. This comes from actual weaving as a threading model you can see sometimes, which is one block of so-called cores, or which are the green things you see here. And these, they like to call them cores and say something like, oh, there's over 10,000 cores in this GPU. These are not really full cores. These are just somewhat fancy algorithmic logic units. So mostly they can do add and multiply and maybe one or two other instructions, and that's it. And you will see that the scheduling and dispatching happens in a separate unit from all of those cores. And this is what GPUs are. They are massive SIMD, single instruction, multiple data models, units. So you do the same thing, exactly the same thing, on 16 or 32 units of data at the same time. And that's also what you can kind of see if you compare just die shots for different GPUs. So on the left we have, I think this is an annotated die shot of an H100, and on the right we have an M1 processor. And what you can see here is this little block here contains 3 streaming multiprocessors, which then contains another 32 cores or something, which is a lot in a small area. This is not completely to scale, but you see the relative scales here. But even if you look at smaller cores here, these are much larger in terms of relative die size, because they are much more complex and can do a lot more things. But this also brings us to a big downsides of this architecture, which is branching is a bit difficult if all your cores themselves can do is multiply and add things. Typically, by the way, forget that earlier, they do the same thing that at the same time. So one instruction is usually a fused multiply and add, which typically corresponds a lot to matrix multiplications or other simple operations. But if you then, for example, have shader code with branching in them, things become complicated. Because what typically used to happen is if you arrived at a point of divergence, you would just discard the minority to be scheduled again somewhere else. So all the work that was done up to that point is essentially lost, and they would have to be run elsewhere. That's, of course, a bit inefficient, which is why you still get a lot of the adage of branching is very bad in shader code. It's still not perfect, but it has improved since then. Since about circa 2016, 2017, all consumer graphics parts shifted to like a slightly different thing called single instruction multiple threads, where if you're running something and you approach a condition, so you have a bunch of work that's run up to a certain point. Let's say we're working with 4 threads here, and let's say half of those are true. What you actually do is you have a register of threads that should be active at a certain point. And then if you encounter a condition, you just disable all of those threads and continue our course for the while and continue stepping along. So the true holding blocks will continue running the branch, while the red ones are just like idle for that moment. And if you then switch to the else, you swap it and exit the loop. And when you exit the loop, you turn everything on again. Or they exit the conditional. That way you don't lose all of the work in front, you did in front, but you still have to execute both conditions. There were a few workarounds to it in the old days, so to speak, but essentially this makes things much easier. But still there's challenges, so a loop will remain difficult. So if you have like one thread that runs for 3 iterations, and a couple that run for 2, and another couple that just run for 1, so it is not exactly to scale here, you're wasting a lot of work not doing anything, because a lot of the threads will be disabled at that point. So, for example, longer running loops or very inconsistent loops are still a problem that will essentially limit your, cap your runtime to the longest iteration. Yeah. So there's still progress that's happening in this hardware, but to reiterate, you have massive units of compute that are relatively simple in their construction and do just a lot of work in parallel, which is well suited for embarrassingly parallel problems. Of course, there's a few things I haven't talked about in these units yet, so let's cover them quickly. The first thing, relatively recently introduced, is specialized hardware for ray tracing, so hardware-accelerated ray tracing. And the first iteration of this is fairly simple. It's just specific units that do the bounding volume hierarchy traversal for you, and the triangle intersection as well, separately. So you have hardware that can handle that very efficiently in single cycles, ideally. And the shaders can then just launch ray probes and ideally very quickly get a response for them, which is what these typically ARC-T cores, or however they're called in the other architectures, are for. And that's a very simple approach to that. As I said, there's a lot more that can happen at that point. So whereas like when it was first introduced, it's just bounding volume hierarchy traversal and triangle ray intersection. It has since moved on a little bit, and we have gotten to the point where there's like much more specialized units in here. So instead of just testing single triangles, you can test whole clusters of triangles and compress them together. If you have very fine geometry, you might also be doing opacity effects, which is the unit. Or something very cool to look at is linear swept spheres, which is a geometry defined by a sphere moving along a linear defined path. which can be used to do ray-traced hair and fur, for example, in real time, possibly. This is from the most recent iteration, so the Blackwell 50 series from NVIDIA, which brings us to the problem. These things also are somewhat prohibitively expensive and difficult to get like at any reasonable price, because there's a lot of incentive of just like shipping this for other things instead of real-time rendering. And I think you know what it is. It's the Gen AI hype we're having currently, which is what the other units are for. We haven't talked about here is beside like int specialized units or floating point specialized units that also get unified in some architectures, we come to the tensor cores. And all I have to say here is it's specialized hardware that does matrix or tensor, which is more multidimensional generalization of a matrix, multiplications in very few cycles, ideally. So this can be somewhat useful in working with like your typically projection matrices, but these units have gotten so big that they're mostly used for neural networks and larger matrix multiplications. But with that little bit of a downer, to put all of this together and wrap this up, let's go back to the beginning. We saw how a CPU renders things, and well, here's a nice representation of how a GPU does things.
4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Well, that's essentially the a good explanation of how this works. It's a massively parallel hardware that's very specialized to do just one thing, which is paint a lot of pixels in a short period of time, and not much else. Well, the robot from earlier would be more general in purpose. And that kind of brings us sort of to the wrap-up. If you want to dig deeper into that now, which is kind of what this talk is about, it's like more surface level covering and finding other rabbit holes to dig into. You can learn by doing it if you want to. So learnopengl.com and vulkantutorial.com are excellent resources to get started with the major graphics interface. Of course, there's also Metal and DirectX, but I don't know good reasons for those. OpenGL is technically deprecated and has been replaced by Vulkan, but it is so much simpler and more abstracted than the nitty-gritty details of Vulkan. So both of these can be very good to learn the basics. You can also just play around and look at things. A lot of the like simple examples I've shown in this talk were just the default free.js examples. And you can play around with them, look at the code for all of them to just see what is possible there. That's a nice resource. And of course, there's a lot of things you can read. For example, there's 3 whole books for free online available from NVIDIA called the GPU Gems, which just cover different rendering techniques in excellent detail if you just like want to dive deep into some specific topics, if you find nice chapters. But with that, essentially we are now done here. So we've looked a bit about how our massively parallel hardware can use our broken down way of rendering things to render massive scenes quickly. Thank you.
So, well, thanks for the talk. Are there any questions from the audience? Hands up or just don't. No questions. Okay.
I mean, I guess there would be a lot of questions here from that one. I mean, we
so.
can talk about a few other things as more to show in like the different examples or anything. So anything comes to mind, feel free.
So we have like 10 minutes.
Yeah.
We could use that. Maybe, do you have an example? So like a real-time example.
I mean, we can look on. Give me a second to change this. I wanna mirror this here. I hope this is okay with the VOC still. Okay, good. So just like looking at, there's a lot of different examples that you can work through here, as I mentioned before, like the Free.js examples that cover different things. For example, like animation is a whole topic we haven't covered here. So this is like inverse kinematics, like the things around that. If you just like have a simple point that you're moving around, there's a lot of transformation that goes around of just like rigging a model and how to move things into it. So inverse kinematics is essentially like a problem-solving thing about like if my arm is here, where should my elbow be? Which is also one of the weird issues you can sometimes see in game if you're walking upstairs and like the legs go like this. That is what's happening there. The inverse kinematics not finding a nice solver. Yes.
Exactly about this.
Yes.
About this point, will be the calculations where the ly has to be. Will that be calculated through matrices as well, or will the CPU be helping there?
Oh, this is usually a CPU-bound thing. So this is like the algorithms involved here are like more branchy and complicated, and you typically don't solve that on the GPU, you solve it on the CPU. But all of those coordinates for the different transformation points, those get like just pre-calculated, but then the GPU handles, of course, the placement. So I'm not sure if there's a good rigging example. What's this like for the blending? No. So if you look at any kind of animation, what typically happens is like these models have bones. Can I visualize them here? No, sadly I cannot. And these bones typically then have weights, are associated to some of the vertices of the model. So you would essentially paint a weight for each of those bones to each vertex. So if I move my elbow, like this only affects my arm. So this doesn't affect my other arm. But most of that is handled CPU side, and like the final transformations is the GPU here. Anything else I can figure out here? Do we have ambient? Oh, yes? Oh.
Was first? Ah, it was just stood here.
So you briefly mentioned that you shouldn't mess with the homogeneous coordinate because weird things start to happen. What are those weird things?
So the key things is like, so one thing that happens here with the homogeneous coordinate going away from one is that translations get wonky. So the differences in like the homogeneous coordinates gets affected to those translations. And also the homogeneous coordinates is somewhat used in the math of perspective matrices, which like are specially constructed, which was out of the scope here. And then things also start to look a little bit more stretched depending on how you construct the perspective or the projection matrix. That's mostly the wonkiness there. But this is just an example. We want to work with the systems and be able to do translation. And if we don't have that, that all breaks.
Yeah, so you mentioned mip mapping as a technique to adjust the resolution depending on the angle and the distance from the camera. And because it sounded like quite a bit more complicated operation than just texture mapping or whatever, I was wondering if that creates any noticeable overhead and how often you would have to recheck that for like a larger scene where the camera is moving through it.
So the just to make sure, like you're wondering if like determining the level of detail is the complicated thing or the sampling. Sorry. I'm just going to do both here. So determining the level of detail is just a side effect of the rasterization process. So looking at this, let's call it this. When you're processing fragments between these, so like as I said, you would move through along both lines in like the horizontal split, and then let's say you're currently rasterizing this line, you then move along this point, and you kind of know like where you are here. But the cool thing is you also you know the value on this point and the value on this point. So you kind of know how far they are apart in screen space, which is essentially like the way you get the derivative. So if they're very close together, you already know this one changes linear from this to this. So getting the derivative here is very simple. And then the second point of just sampling the point is something the GPU is specialized to do. So there's like certain texture units that literally do like this trilinear interpolation as typically like abstracted as a single function call. So what it would look like in a shader is literally just you say texture and this is my coordinate. And per default, this will just do the interpolation for you if you specified it around that. So this is just, you fetch 8 points from the texture, and then interpolate the top and bottom ones, and then interpolate between them. And the interpolation is just like a fused multiply add, and that's what the GPUs are for.
So, okay, last minute, and with that, we are closing the Q&A. Crypticcelery, could you once again show your details? Where can people reach you?
Yeah, I'll still be around the GPN for the whole weekend, but you can also reach me via DECT or on Fedi, or just talk after this, or if you see me around. Happy to talk about more of this, because I really like this topic. So, again, thank you.
Okay, thanks to you, thanks for the talk, and the last round of big applause.